Okay, welcome back, everybody, to the last topic of this current unit on similar polygons. Today we're going to talk about applications of proportions, so word problems, and then how the scale factor of two similar polygons relates to the perimeter of those polygons and the area of those polygons. So first of all, let's talk about the story problem. So we're going to talk about indirect measurement. So that's when it's not practical to measure something directly, like the height of a building. You can set up a proportion and then get that height without actually physically measuring something. So indirect measurements using proportions to measure an object. And as an example of that, I've drawn this figure here where we want to find the height of the flagpole. So you see there, the flagpole, and the height is h. That's what we're going to look for. The shadow that the flagpole casts on the ground is 14 feet 2 inches. So we got mixed units here we're going to have to deal with. Then you see a stick figure also, who is 5 feet 6 inches. And that stick figure casts a shadow of 5 feet. And so what we're going to do is we're going to change all these numbers into inches, and then we're going to be able to work easier than if we had mixed inches. So if you look at the two triangles, they're similar because they both have a right angle, and then because the sun's rays are shining down at the same angle, we also have a couple other angles here that are congruent, but the triangles are similar by angle, so we can set up a proportion. Before I do that, though, I'm going to change everything into inches so that we're not mixing up the units. So this 5 feet shadow, 5 times 12, that's going to be 60 inches right there. The person's 66 inches. And then the shadow is 14 times 12. We get 12 inches in a foot, so 14 times 12 plus the 2. So this is 170 inches. So it's important that all the measurements are giving in the same units here when you go to write our proportion. So we know when you write a proportion, we like to start with an empty proportion and fill out the spots. So corresponding sides would be the 66-inch figure, so 66. It's going to go over the height of the flagpole, so that's h, that's what we don't know. So it's going to be equal to the 60-inch shadow over the 170-inch shadow. So when we solve this proportion, we're going to have the height of the flagpole in inches, and then we can change it back to feet and inches if we want. So we'll go ahead and actually what I'm going to do is I'm going to cross off some zeros here, so that gives us 66 over h equals 6 over 17. Before I cross multiply, just makes the number smaller. So we got 6h equals, so we got 66 times 17, 1122, and divide by 6. So it's 187 inches now. Okay, so if we want to change that back into feet and inches, you'd have to divide this by 12. So divide by 12. So it's going to be 15 feet. And then we'll just take 15 times 12, which is 180. So that means we had 7 inches left over. So 15 feet, 7 inches is the height of the flagpole. Okay, so that's an example of indirect measurement. Okay, so you can also use proportions in similar figures in scale drawings, like on a map. When you see a map, obviously on your Google Maps or whatever map you're using, that's obviously not a full-size drawing of the road, and so they have a scale drawing. So a scale drawing is when you want to represent an object that is smaller or larger than actual size. So you can actually do this on a larger scale too, if you want to draw a scale model of, let's say, a molecule or an atom or something like that. Okay, so here's an example of a word problem that we're going to use for a scale drawing. On a Wisconsin road map, Kristen measured a distance of 11 1/8 inches from Madison to Wausau. I think that's a city probably. The scale of this map is 1 inch to 13 miles. What is the actual distance between Madison and Wausau to the nearest mile? So we're gonna set up a proportion. Just be consistent with your proportion. So you got the scale of the map is 1 inch. So I'm going to actually write the units on here so I remember. So 1 inch over 13 miles. So that means on the other side of the equal sign, I have to be consistent, put inches on top there. So 11 and 1/8 inches, I'm going to write as a decimal. It's 11.125 inches. And then we'll just say M is for miles here. So it's just a matter of cross multiplying. And that'll give the real distance approximately between those two towns. So it looks like 1 times M, or M, equals 11.125 times 13. So 144.625. And they want this answer to the nearest mile, so we're going to round it up to 145 miles. So there's a good example of a scale drawing using proportions. Okay, now we're going to relate the scale factor of two similar figures to the perimeter in the area. So you see in the figure here, two similar triangles. They're both right triangles. They both have a common angle there. And so we know that the two triangles are similar here. And so the similarity ratio you can get from any pair of corresponding sides. So 3/6 are the two bottoms, 4/8 are the two right sides, and 5/10 are the two hypotenuses. But no matter which fraction you look at, they all reduce to 1/2. So the scale factor or similarity ratio of the two figures is 1 to 2. Now, if you relate that to their perimeters, the perimeter of this first figure, just add up all the sides, it's going to be 12. And then if you add up all the sides of the second figure, it's going to be 24. So the ratio of those two perimeters is 12/24, which is 1/2. So notice that the similarity ratio and the ratio of the perimeters is exactly the same fraction. Let's take a look at the areas of the two figures. So the area, remember, of a triangle is 1/2 times base times height. So 1/2 of 3 times 4 is 12. 1/2 of 12 is 6. So that's the area of that first triangle. Let's get the area of that second triangle. So 1/2 times base times height. So 1/2 times 48 is 24. So the ratio of the areas is 6 to 24, which reduces to 1/4, which is 1/2 squared, right? 1/2 times 1/2 is 1/4. So what we can say is, if we compare the ratio of the areas with the scale factor, it's actually the scale factor squared is going to be the ratio of the areas. The ratio of the perimeters, again, was the same as the scale factor. Okay. So that's going to lead us to a theorem, and then we'll do one more problem. We're not going to prove this theorem. This is called the proportional perimeters and areas theorem. And what it says is, if the scale factor of two similar figures is A to B, then the ratio of the perimeters is the same. It's A to B. And the ratio of the areas is A squared to B squared. So again, kind of easy to remember. You got two similar figures. They don't have to be triangles, but any similar figures. If you know the scale factor is A to B or whatever, that's going to be the same as the ratios. And then the square of the scale factor is going to be the ratio of the areas of the two similar figures. Okay, so we'll do an example using that idea. So in my last example, you see two triangles there, and triangle RST. So the first triangle is similar to triangle UWV. We're given that. We're given that the bottom side of that first triangle is 16 and the bottom side of that second triangle is 20. So since these two triangles are similar, we're going to be able to use that as your scale factor. Okay, so I'm going to calculate the scale factor right now. So the scale factor is just the ratio of one pair of corresponding sides, so 16/20. Divide those by 4, that'll give you 4/5. So scale factor is 4/5 between those two figures. And now they're asking us to find the perimeter and the area of that second figure. We have the perimeter and area given in the first figure, but we're going to use that perimeter along with the scale factor to get the perimeter of the second figure. And notice we can do that and we don't even know what the sides are. So we're going to set up a proportion using that scale factor. So here's your empty proportion. Let's put your scale factor in there that we know is 4 to 5 from the one pair of sides that they gave us. And remember, the ratio of the perimeters is the same as the scale factor. So we're going to put 36 as the smaller of the two perimeters. So that's going to be on top of your fraction. So 4 over 5 equals 36 over, let's say, p for the perimeter of that larger figure. Let's go ahead and cross multiply and solve. So 4 times p equals, so we got 36 times 5. So 36 times 5, that's going to be 180. And we'll divide to get that perimeter of that second triangle. Divide by 8, that's going to be 45. And we're going to write that in feet. Okay, so the last part of our problem is we're going to find the area of this second triangle by, again, setting up a proportion. But this time, when we set up our empty proportion, we're comparing the areas of two similar figures. And we said that those areas, the ratio of those areas is going to be the square of the scale factor. So we're going to have to square that 4/5. So when you square 4/5, you get 16 over 25. So that's going to be in our proportion, the 16 over 25, the square of the scale factor, because the ratio of those areas. So the area of the smaller figure, remember, was the 48. So we're trying to find the area of that larger figure. So the 48 then goes on top of this other fraction. We'll just call that last spot area, A for area. So we got 16 times A. Let's do 48 times 25 here. So 48 times 25 is 1,200. And we'll divide that number by 16 to 75. And remember, that's going to be an area, so that's square feet. Okay, so there you have it. So just to kind of recap what we did in this last lesson in this unit is we showed a couple examples of using proportions to solve word problems. And then very importantly, we saw the connection between the scale factor of two similar polygons, which is going to be the same as the ratio of their perimeters, but the square of the scale factor of the two similar polygons is going to be equal to the ratio of the areas of the similar figures. Okay, there you go. Let's go ahead and get some practice with our assignment.